A large chunk of the forces chapter is about using Newton's laws to explain motion, to explain what's happening. Newton's first law doesn't tend to get as much, often abbreviated instantly as N1, but remember, in kind of written descriptions you can't use abbreviations. But just to remind us, that's an object, right, any object will remain at rest or move at a constant speed in a straight line. We could just written in a constant velocity, because that includes the idea of constant speed and a straight line, unless there's an unbalanced force acting on it. So it tells us what happens if the forces are unbalanced, right? Something's going to change. It's either going to change speed or it's going to change direction. If it was at rest, it's going to start moving. The opposite is if the forces are balanced or if there's no force. It's just worthwhile clarifying that idea that those two are equivalent to each other. Balanced forces are equivalent to no force acting on an object. Newton's second law, though, is the one that we'll spend much more time on, but it's actually the simplest of the two. It's given in the formula sheet. It's written in the formula sheet as F equals ma, but I want to stress this idea of fun equals ma. It's the unbalanced force that's key. So for instance, in a car, it's not the engine force, it's the unbalanced force, which might be the engine force take away frictional forces. Right, or there might be aspects of gravitational forces involved if a car's going up or down a hill and so on. You've got to take account of all the forces. So the formula here is very simple. You've met it before, familiar with it. But a large chunk of this unit then is just practice at using this in different situations. So that even if a strange situation comes up in the final exam, you have a good idea of how to approach. And the basic idea of how to approach any problem involving force and acceleration, Newton's second law, is to draw a free body diagram. Don't spend ages making it look like the object you're interested in. A circle or a square will do. And then what we want are only the forces that are acting on that object. Right? No other objects involved. The only impact that they can have on the object that you're interested in is by applying a force, and therefore they would appear. So for example, if we look at a rocket taking off, we could have an arrow to represent the thrust. Now if you're doing these free body diagrams because the question has asked you specifically, then you should label that out in full. If you're just doing working for your own calculation, then a T would do. Notice we want the arrows to actually meet the objects and not just kind of floating in thin air beside them. The object, the rocket, would have weight pulling it down. Remember, it's not gravity. Right? Gravitational force would be acceptable. And possibly air resistance. Make sure my arrow touches the object. Except we'll see that in most examples we're going to neglect air resistance. And one way of getting around that is often in the questions you get things like at the moment of launch. Well, at the moment of launch the rocket isn't moving, so it doesn't have any air resistance at that point. And once again, only the thrust and the weight. So in general, drawing these diagrams is really important. Everything is only analysed in terms of the forces acting on it. And all the different examples, different situations we'll look at, they all come back to the same idea. Draw a diagram, and then beside that diagram, write what fun is in that specific situation. So to look at the most complex thing that we could get, if we included air resistance, that would be T because it's going up the way, minus W because it's going down, minus R because it's going downwards as well. And then we can use that along with the fact that fun equals ma to solve the problems. But this bit here, writing what fun is basically the key. I mean, plugging numbers into the formula fun equals ma is not difficult. But what is in the different questions is working out, well, what is fun in this particular situation? So if this was a rocket taking off like that, okay, and we'll look at some worked examples over the next few slides. Before we look at the worked examples, one other definition we need is the definition of the Newton. So using this formula, fun equals ma, we get the idea that 1 Newton of force, so 1 Newton is the force, and if you look at the right hand side of the formula, ma, which causes 1 kilogram to accelerate at 1 meter per second squared. So if we look at a worked example from your notes, we've got a question about a rocket with thrust T acting up the way. Now it doesn't mention the weight in the question, so you've got to remember to fill that in for yourself. As soon as you recognise it's to do with vertical motion, then weight is going to be significant. And the key in this situation then is fun equals T minus W, and it mentions at launch, so we know there's no air resistance. So the key is fun equals T minus W. We can work out W first of all before we go any further. So we know that W equals mg equals 8,000 times 9.8 equals 78,400 newtons. And we know the value of T, we know the value of M. So I've now got enough to solve the problem. So we write our fun equals T minus W, which is specific to this problem. But we know that fun is also equal to MA. So where we had fun in the formula, we can now write MA equals T minus W. And now we can start substituting. 8,000 times the A that we're trying to work out is the thrust, 200,000 newtons, minus the weight that we just worked out. Plug in the values, rearrange to get A. So simplify what you can. So that side's going to be 121,600. So A will equal 121,600 divided by 8,000, and we get the final answer. It's 15.2 meters per second squared. Have a think, is that a sensible answer? It's quite a large acceleration actually for a rocket, but maybe that's not that surprising. Rockets are big powerful things. If you had a balloon, for instance, with that sort of acceleration, I think you'd be questioning whether you've made a mistake somewhere in your working. One other thing worth mentioning about rockets is as they take off and burn up their fuel, then their mass decreases, and that has the effect therefore of decreasing their weight, and so the unbalanced force increases, and also that unbalanced force you're dividing by a smaller mass to get the acceleration. So you have two things there which cause the acceleration to increase. The other reason the acceleration of a rocket can soon increase is that as you get further away from the Earth, gravitational field strength decreases. You also have some competing effects about air resistance, but because you have some competing effects, I think they're worth avoiding. So basically, as it gets faster through the air, that would increase air resistance, but then the atmosphere gets thinner eventually. If you leave the atmosphere, there's no air resistance, so you do have kind of competing effects there. In the next examples, we'll look at the idea of someone in a lift and think about the forces acting on them. So here's our someone. Remember, we don't want to particularly make it look lifelike. You're standing in a lift. The earth is trying to pull you down. Your weight is still acting on you. You don't fall because the floor is pushing you up. We can call that a reaction force, right? But I like to use R because if you're standing on a set of scales, it's that force that the scales are going to measure. Now, as we'll see in a second, when the lift station, if you're standing just in a normal floor, then R will equal W, and that's how scales read your weight. Right, but that's a special case, they don't always read your weight, as we see in a wee second. So as usual, the same method applies. Fun is R minus W. So we draw a diagram, we get an expression for fun in that particular case. Then using Newton's second law, we can say ma equals r minus w. And what this does is enables us to link the acceleration of the lift to the value of r. M is fixed, and because of that, w is fixed. It's just mg, remember. And basically what we can do is look at common situations then. If you're at rest, then a is equal to 0. So if we look at that formula there, if a is equal to 0, then ma is 0, i.e. r minus w equals 0. Or rearranging that, we get r equals w. But that's also true for constant velocity. By definition, the acceleration is equal to 0. So r minus w equals 0 as r is equal to w. So when we were in the lift, we had that initial acceleration of the lift when it started moving, but then once it settled to a constant speed in between the floors, your weight reading went back to, this reading in the scales went back to being your weight. So they're grouped together. We can also group together some other motions. Right? When you first get in a lift, we'll make it a wee bit easier this time and start at bottom floor. If you accelerate upwards, then A is positive. Now the other motion that can give you a positive acceleration is decelerate down. So both of them give you A is positive. That means R minus W is positive, and that can only be the case then if R is greater than W. So when the lift is accelerating up, right, so if you get in a bottom floor and press the button to start going up, then the reading in the scales will be greater than your weight. And that's what your body senses. You feel heavier at that point. When you're going down, so when you're already moving and you start to slow down as you approach a bottom floor, then once again you feel heavier. The reading in the scales is greater than the weight. Basically, in both of those cases, the floor's got to push you up more than your weight in order to produce the change that's needed. Right? Either to speed you up if you're going up the way, or to slow you down if you're coming down the way. And the last types of motion we can group together. If you decelerate up, okay, so if you're in your lift and you're approaching a top floor, as you start to slow down, then A is negative, but accelerating down has the exact same effect. So when you're in a top floor and start moving down, in both of those cases A is negative, so R minus W must be negative, i.e. R must be less than W. And at that point the reading in the scales and how you feel is lighter than your normal weight. Next we'll look at the idea of tension. Look at some worked examples to do with that. But first of all, tension is a force which exists when you join two objects together where one is pulling at the other. So for instance in ropes, if they're joining things, tow bars between a car and a caravan, couplings between train carriages. These are the kind of things that come up. And basically we can just apply Newton's second law in the exact same way that we've been doing, with one slight twist. So for instance, if I have a 3 kilogram block being pulled along by a 10 kilogram block with a force of 20 newtons. So that's our kind of situation. The tension will act in the join to pull this left hand block to the right, but that also has the effect of pulling back on the first block. So this is basically a Newton's third law pair, that the force that the 7 kilogram pulls the 3 kilogram forward is the same as the force the 3 kilogram pulls the 7 kilogram backwards. Equal force in opposite direction. But we'll revise Newton's third law in another chapter. But so what we can do now is apply Newton's second law, but the one slight twist is that we have the idea that we can apply Newton's second law to a whole system or to individual blocks within that system. The whole system has a mass of 10 kilograms and is being pulled along with a force of 20 newtons. The tension doesn't appear in that because it's what we call an internal force, and basically those pair of arrows would cancel each other out anyway. So, as usual, our method, draw a free body diagram, write an expression for the unbalanced force in that situation. And then you can use MA is equal to that, and then in this case 10 times A is 20, gives us the acceleration of the whole system. But if the system isn't falling apart, which we assume, then the individual parts within that system must have that same acceleration as well. So now if I look at the 3 kilogram block, the free body diagram for it, well, it's 3 kilograms, and it's being pulled, if we go back to the original diagram, it's being pulled by some sort of drawing, a rope or something like that. So the only force acting on it is the tension. There's been no friction involved in any of this. So in this example, Fun equals T, i.e. MA equals T. This time we know the mass, and now we know the acceleration. So we can rearrange to get the tension is 6 newtons. Now I could have got the same answer if I'd considered a 7 kilogram block, but it's a wee bit more complicated because it's got both the 20 newton force and the tension pulling it back. So it's always easier when you've got objects pulling another to consider the one being pulled. It's usually got less forces acting on it. The exact same logic though does apply to one object pushing another. So if I had the 7 kilogram pushing the 3 kilogram, the whole thing being pushed with 20 newtons, then I could get the exact same reasoning all the way through, deal with the whole system, get the acceleration as 2, and then when I came to dealing with the 3 kilogram on its own, what I'd have is a pair of Newton's third law forces at the force. If I call that A and B, it's probably a bit clearer. On object B, then what you've got is the force of A pushing it. So you can work out that force between the two, just in the exact same way as we worked out the tension. Another common situation that comes up involving tension is the idea of a tethered balloon. So for instance, if you take a helium balloon which would be trying to float away and somebody's holding it in place, then the forces acting on it are what we call upthrust. I'll just label that with a U for just now. Basically the buoyancy force of the balloon. The balloon would have a weight, might be very small, but it does have a weight. But the key point for us really is the idea that the tension there's holding it in place. And if it's been held in place, then the forces are balanced, or the acceleration is 0 either way around. You get the same idea. And Fun is U minus W minus T. And if the forces are balanced, or the unbalanced force is 0, and we can set all that equal to 0, and then I can take T over into the other side, and I can say U minus W is equal to T. If I now cut the rope, then I'm getting rid of the tension. The balloon will then float away. That upthrust won't have changed. That weight won't have changed. But it'll now be unbalanced by an amount equal to the tension. That's what we've taken away from the situation. So that's now how unbalanced it's going to be. So now, with the tension taken away, the unbalanced force is equal to U minus W. But I don't actually need to know those values because as we saw up above, that is equal to the tension that was tethering it before. So the unbalanced force when you release the tension is equal to the tension that was keeping it balanced in the first place. And you can now go and apply your MA is equal to T and solve for whatever you need.